Hey, hello everyone. This is a video intended to tackle the content we couldn't finish on the recitation and to solve some of the issues we were having when we were making the mesh. For this video content, what I want to cover is the following. We will be going through using Crane, but we will tackle in different ways. First of all, we will go from flat to fold. And this flat to fold, we will be using grasshopper entities. The second part of this video, we will go from flat to fold using Rhino entities that we will import into Grasshopper. And the third part of this video will be using we will be importing elements in 3D that can be developable or non-developable, and we will use the constraints of Crane to satisfy whatever needs we have in terms of shape, but at the same time we will be making sure that everything is developable. For now, we will go through the first part of this component, which is flat to fold using Grasshopper. And the easier example we have for this would be a simple degree 4 vertex. So to do so, I'm going to be using some native tools from Grasshopper, and later we will use Crane to import the mesh at the solver. And I want to use this tutorial for the class for those who are not familiarized with Grasshopper as well, to start making some elements. So for example, we will start putting like some fun inputs. We can put something like a control knob that, for example, we will name as V1. And ideally, I want to have some points here in the center that if we just control knob them, we will have a visual way to change the angles of this degree 4 vertex. And this, so if I put a panel, you can see that this knob will give us numbers from 0 to as many revolutions we give. So for example, if we want to match a circle, we can just like have this value of knob multiply by 2 pi. Such as if we put a point here and we give this point some radii. So for example, imagine I want to put a radii from, like, we want to control the radii of our vertex from 1 to 15 in Grasshopper. I will double click and put 2 points, 15. So we will have a slider right now that shares from 1 to 16. So I will link this to, for example, the y component. So now we have a point that goes from 0 to 15 in radii. And as we said, we want to rotate it. So we want to use rotate. In G, we read that this is the geometry. This is the point. So this is the rotated point. And how much do we want to rotate it? 2 pi multiplied by the knob. So now, theoretically, it's rotating as we rotate the knob. As we can see, it's rotating in the other direction we're plugging, but this is easily solved by just putting some negative value. So now we should be rotating as we're rotating this knob, no problem. And this is a fun visual way to start adding points. So we can clean this up because right now this is looking a little bit messy. So factor 2. So for example, if we are in this situation in which we have here a slider that we actually wouldn't like to interact with, we can delete it. And if we right click this end, we can set a number that will be hard code. So as soon as we put 2 and we commit the changes, this n is now equal 2, and we don't have any annoying factor coming here. So we have this point, we have this rotation, and we can make all this a component. And because of, I'm going to copy all this to make 4 vertices, but the radii is going to be constant. This resting will be unique entities. I will hide this. And I am going to make a group. Just looks visually a little bit more appealing and organized. And from this group, I will now copy, and I move it here, and I move it here, and I move it here. And now we can right click, edit, and this is going to be called V2, vertex 2. This will be called vertex 3. And this is going to be called vertex 4. Now we have vertices that will define our degree 4 vertices, and we will need to start adding points and lines. I want to use with you what we were playing in the first with in the, so well, first of all, instead of calling this y coordinate, we can change this name for radii. So now all of them will move accordingly with the radii, and all of our knobs will be moving as well accordingly to this. On the first recitation, we talk about using Python. So for example, right now, I wish I had a grasshopper component that will ideally draw all the lines from the center to every vertice and all the lines for the perimeter. And because of we're going to use Crane and we are going to use as input mesh from C lines, we know that we need to have a boundary. We know that we need to have a group where all the mountain will be, a group where all the values will be, and a value of the valence, which we will go through, which was the origin of our problems last recitation. And I think I figured out why, so I'm happy to talk through it. So we can totally do that using Python. So I'm going to open a Python script one here, and we know that as inputs, I'm going to take 4 vertices, and I'm going to call them V1. I'm going to call them V2, V3, and V4. And I also know that the type of hints that we are getting is, this is important. If we put a point 3D, then we can use functions that we wouldn't be able to use if we don't do this, just because we want to access coordinates. And this is a good way to access coordinate faster as well. So we know that this point, for example, will be V1, V2, V3, and V4. And as output, we know, well, we will use out for debugging because it's, I like it. I think it's comfortable to have your debugging nicely readable. And as outputs, I'm gonna have 3. Well, we're gonna have 4 because if we're gonna use boundary, we are gonna have as an output all our mountains. We're gonna have as an output all the valleys, and we will hard code valence. And so everything will be just blindly code to these other components, such as we can be as flexible here as possible. And now let's go through Python. We open the window here in Python, we delete, and the first thing we always do is like import Rhino script syntax as rs. And we can, for example, set a couple of things. For example, we want an empty list for our boundaries, an empty list for our mountains. Our values is always 1 because it's a degree vertex, so we can even hard code it if we want. And we can set, like, for example, origin is going to be equal to 0, 0, 0. And we can make even, for example, something that is going to be helpful later. Let's start hard coding. So, for example, we know that our valleys, which will be an output called V, is going to be only composed by one line. And it could be, for example, for vertex 1. So we hard code that V is equal to rs at line that goes from origin to V1. And as soon as we clicked, we're going to see that a line should appear here. And we can check, we have a line by curve elements, and it's this one. And as soon as we move vertex 1, we should see that line as well moving with us. So that's good. And we can keep going. We know that mountains will be composed by V2, V3, and V4 joined by the center. So we can do the following. We would put, like, for vertex in V2, V3, V4, we can do mountains append errors at line origin vertex. So this for loop should give us, oh, they jumped apps. We don't want apps, and actually we want, my bad. This bracket. So now we have our mountains, we can see should be a collection of 3 lines. So we get, and we can start playing with the position of those vertices. And for the boundary, we want all of them joined together. So we can do a vertex list is equal to v1, v2, v3, v4. So for e range line vertex list b dot hand versus line vertex list I-1 to vertex list I. And now as we run it, we will see a boundary layer. Join it all together, and we can confirm that our B component is composed by 4 different lines. And as last element, valence is empty because we haven't declared it. So we can set that valence for this one is going to be equal to 3. Basically, valence value, you know that Crane Solver wants to have a mesh that resembles the paper you're going to fold. And meshes can have different forms. Rhino only works with 3-point vertices, triangular vertices, or quads, 4-point vertices. Valence, it will be the maximum number of vertices that your mesh is going to see. In this case, we're going to be working only with triangular vertices. So valence 3 is what's going to work for us for this case. And here we can directly join everything together. And we can get it to the CMesh. We can start see stuff in our CMesh composed by our mountains and our valleys. The last thing we need to do will be to assign a full speed that will kind of depends on the speed of your computing of your computer. So for me, something between 0.1 and 1 should work. So we can test. And rigidity, Something from 1 to 10 we can also play with. So theoretically, if I select this and I Alt Solver and reset, we should be able to start folding our vertex. And now we can see that it's working. You will see that if we change our base molecule here, it's not updating. That is because we need to reset. And now we can fold it again. So this is a great case in which I can introduce you with the concepts of constraints, right? Imagine that we know that two lines will always form a plane, and we can call this plane the osculating plane. So we can enforce that these vertices do coexist in the same XY plane that we are seeing here. And that is very helpful because this is going to help you in the future to start setting constraints, where Crane gets very interesting. So here in constraint, we're going to apply on surface. And we see that as inputs, we take C mesh, the surface. I mean, if we leave here, it should tell us what it is. The vertices IDs, everyone stick around. And S is the strength, which let's see what happens if we leave it empty. So our C mesh is this one. Our surface is going to be the XY plane. And which are the vertices ID? Great question. That's why we have a component called preview, which you can say vertex IDs, and we can import it. And now we know that we want to be glued 4, 1, and 0. The way to do this is that you put a panel and you put 4, enter, 1, enter, 0, enter. Click out, and you right click and set multi-line data. This will give you a constraint is enabler now, such as when we input here and we reset, it went crazy. So we have a problem. Let's see what it is. Disconnect. Oops. Reset. Fall and fall. We're happy. Which mistake did we did? 4, 1, 0. Let's reset it. Let's bring it back again. And still. It will disconnect it. So reset. Oh, I think I know what it is. It's because it's not on surface, it's on plane. My bad. We're gonna just like ignore this one. We don't need this. So I'm pretty sure that now we're good. So now we can see that as we fold, we are keeping these two vertices on plane. It was my bad because it's on surface, will allow you to do this, but given any chosen brep you select here from Rhino Compute or something you've done from Grasshopper. So we can increase our speed of folding, but we see now that we have degree for vertices with arbitrary radii folding. So this is all for the first part of the video, which is 1.1 flat to fold using Grasshopper.